use the property of equality for exponents. And then if we couldn't use the property of equality for exponents, we changed it to logarithmic form, which is why the log exists, to solve for exponential equations. So we have square root functions to solve for quadratic functions. So there's reasons why all these math functions exist in the world, so that you can solve one function with the other function or apply that function to another function. That's usually how math works. Learn something and then you continue to apply it and use it. So today we're going to talk about the property of equality for logarithms. If there's one for exponents, there's got to be the same property for logs since they're inverse functions. We will review what an extraneous solution means. So we talked about that first back in chapter 4. Actually, we talked about it in chapter 1 with absolute value functions, a little bit in chapter 4, and then in the last chapter with the radicals, they were extraneous solutions. So there's going to be extraneous solutions with logarithmic functions as well. So we're going to look at those. And then pretty much we're just going to see if we can solve some logarithmic equations. Really is, I would say, a short day of notes, and there weren't any homework questions that I saw on the form. Are there questions that you would like to ask or go over with the exponential homework, the equations? Were they pretty straightforward? Good. Okay. Hello. I might come back and look at it if that's all right with you. I might be able to see. So if you want to take out your packet, if this is like the last slide of the packet. The 1/3. So 6 is an exponential number. Instead of dividing by 1/3, multiply that. So you, yes, you cannot multiply these together because this is an exponential. Exactly. Yep. I'm glad you asked. All right. So, as I said, last page, this is page 22, actually, it's not quite the last slide. We did the top half, these logarithmic, actually exponential form that we changed to logarithmic form. We did this top half on Friday. You will need a calculator to solve some of these, but not all of them. Actually, I'm trying to think. I don't think you'll need a calculator today. Maybe 1 or 2, but I think all of these work out pretty nicely for us. So, property of equality for logs say that if b, x, and y are positive, and b is not equal to 1. And it can't equal 1 because as an exponent, if you have the number 1 to any power, it's not an exponential function because 1 to any power equals 1. So therefore the base can't be 1 either if it can't be written as an exponent to be an exponential function. So it says b, x, and y are positive numbers, then the log base b of x equals the log base b of y if and only if, what do you think goes in the little blank? So if the log base b of x is equal to the log base b of y, that happens if and only if x is equal to y. So 2 logs of the same bases are equal to each other if the values for x and the y are the same. So property of equality, equality means equal. So it says here, if the log base 3 of x is equal to the log base 3 of 8, then x has to equal 8. Because if I plug an 8 in here, that's the only value that's going to keep them equal. So the log base 3 of 8 is only equal to the log base 3 of 8. Can't be equal to anything else. Property of equality. So if x equals 8, then the log base 3 of x equals the log base 3 of 8. Again, these are conditional statements, if and only if. So that means I can write it one way, or I could switch it and say, hey, I'm giving you the x value, then the two logs must be equal to each other as well. So a conditional statement of if and only if means either way you read it, one way versus the other, both of them would have to be the same. So if you look at the first group of examples, and I think there are two of them here, these two examples deal with the property of equality. Notice part A says the log base 7 of, and then it's grouped in parentheses. So all of that is contained together. 6x minus 16 equals the log base 7 of the quantity x minus 1. How do you think you would solve for x? And why? Ella? And why can you do that? Yeah, because of the property. So the base has to be the same. If the base isn't the same, the property of equality does not work. But if the base is the same, then you want the quantities next to the log to be equal. So if they need to be equal, then you set those quantities equal to each other. So set them equal to each other, add the 16, subtract the 7, not the 7, the x. So if you do that, Jaden, you end up getting 5x. No, and this is a 1. Jeez. So she said 5x is equal to 15, so then x is equal to 3. And we could do a little check. If you plug in 3 for both of these, it does hold true. 6 times 3 is 18, minus 6 makes 2. And on the other side, 3 minus 1 is definitely 2. So you can check to make sure that it is the property of equality that the two are true. Questions? Pretty straightforward, property of equality. Looking at part B, we have the log base 5 of 4x minus 7 equals the log base 5 of x plus 5. So again, as long as the bases are the same, then you can use the property of equality. So set the expressions after the log equal to each other. And again, we're subtracting x and adding 7. So 3x is equal to 12, or x would be 4. Pretty straightforward for those, property of equality. This only works when you have one log equal to one log of the same base. If that is not the case, then you don't have equality of logs. So obviously that's going to be the case for a select amount of times, but not every time. And the remaining 6 examples on the other page are different log equations that we cannot use the property of equality for. So in example 4, it says use exponential form of the logarithm to solve each equation. Again, a log and an exponent are inverses. So if you cannot do anything with the way the log is written, then you can always change it to the other form to see if you can solve it using the inverse form. So in this case, if we have the log base 5 of 3x minus 8, that's in parentheses, and then it's equal to 2. We can change this to exponential form and see if that helps us solve the equation. Remember, when you're writing it as an exponent, the base is 5, the exponent is 2. It's going to equal 3x minus 8. So the base, still the base. The exponent is on the other side, equals, and then the entire quantity, 3x minus 8. So if you cannot solve it in log form, we can try and solve it in exponential form. Gabby Soul, 5 squared is 25. And then Gabby, when you solve this, you add 8 and get x would be 11. Yeah. So write it in the inverse form, which is the exponential form, and then solve for x, which is essentially the same thing that you did for the second half of your homework. You had exponential form. You couldn't do anything with it in its exponential form, but we could write it as a log, and we could solve for x as a log. So part B, the log base 4 of the quantity 5x minus 1 equals 3. So Riley, how could you write this one as an exponent? 4 cubed is nice. So when we add 1, we get 65 equals 5x. What is 65 divided by 5? Excellent, nice job, 13. So that seems pretty straightforward too. Questions? So property of equality is when you have one log of the same base equal to one log with the same base. This is just using exponential form to solve the log function. So you're using the inverse form to solve for x. And it still works. Like if we plug a 13 in here and then we would evaluate it, it would still work for us. So the last group of problems, just say to solve the following equations, and then it says check your extraneous solutions. And I want us to kind of think about the extraneous solutions. For a minute before we look at the examples. So what makes an answer extraneous? So think about why extraneous solutions happen. Or what makes an answer extraneous? Why would it be extraneous? What's this word mean? So we know solution is an answer. But what does it mean for it to be extraneous? Think back to the last chapter.
I don't know, like, the wording part, but like, isn't one of my solutions that are like, I don't know, it could work, sometimes it also can't, but may not work, I don't know how to explain
Yeah. It could work, but it might not work. So you might get 2 answers, and one of those 2 answers may not work, which makes it extraneous. I'm going to say it does not hold true when substituted into the original problem. And that's the key. It has to go back into the original function. I think I spelled that right. So you have 2 solutions. One of them doesn't work, may not work, when it's substituted back into the original problem. So it doesn't keep the equation true, the left and the right. Now, for log functions, specifically, because each function is different, the domain of the log function is from 0 to infinity. Remember, the log function has that vertical asymptote on the y-axis. So the graph only exists from the y-axis to the left, or when the x values are positive. So extraneous solutions in log functions happen when values make the log 0 or it makes the log negative. So I'm going to put a little asterisk here. So we're going to be looking for values that make the log negative or 0. So you can't just say, oh, this is going to be extraneous. You have to specifically look at the x value and the original function that you're given. So does it make the log, this part right here, 0 or negative? So if the number next to the log becomes 0 or it becomes a negative number, then that answer is extraneous. So whatever's after the log, we have to plug that number in to make sure that it's not negative and it's not 0. So looking at the first example here, this equation, the log of 5x plus the log of x minus 1 equals 2. So thinking about the properties that we have discussed in the last few sections, what do you think you would do first to try and solve this equation? Condense. Yeah, and that's a good word too. There's a plus sign there. And right now we have 2 individual logs. So we can pull them together by condensing it into one logarithm. And Brooke, condensing it when it's addition, how would you actually pull those together? Excellent. So to condense the logs, the property is called the product property of logarithms. So if 2 logarithms are being added, you condense them by multiplying the quantities after the logs together. So we're multiplying the 5x and the x minus 1 together. So you're not adding them. That's not the property. Yes, it's an addition of 2 logs, but to condense the logs, it becomes multiplication. Remember, it's the exponential property as well. So if I'm multiplying exponents, I add the exponents together. So this is the opposite. We're adding logs, so we multiply them together. And then you actually want to do the multiplication. So let's perform that multiplication. We have 5x squared minus 5x. Both of those are grouped together next to the log. So I can't move one of them to the other side because they were both with an individual log. So when you combine them together, they're still both with the condensed log. So now we have the log of 5x squared minus 5x equals 2. What do you think you would do next to solve this? Jaden? Yeah, we're going to write it in exponential form. Jaden, if the base isn't there, it's implied to be 10. So really, this base is a 10, even though it's not there. It's implied to have a base of 10. So after you condense them, then we're going to write it in exponential form. So again, the base is 10, the exponent is 2. It's equal to the entire quantity, 5x squared minus 5x. And we know 10 squared is 100. All right, so we got rid of the log, we got rid of the exponent. Now I have an x squared. Jordan, what do you think we would have to do if we have 100 equals 5x squared minus 5x? So set it equal to 0. And then, Jordan, what would you use to solve this? Yeah, we would factor it. So first, when you factor, if there's a GCF, take it out. And these are all divisible by 5. So let's pull out the 5. That makes factoring a lot nicer. And then when we factor, we're thinking about the negative 20. the two numbers that combine to be a -1 from the values or the factors of 20. So Alyssa, what two numbers multiply to be 20 but combine to be a -1?
4 and -5.
Excellent. So we got a GCF. She said 4 and -5. This is the shortcut factoring. There's not a coefficient in front because we factored it out. It's just an x squared. So a +4 and a -5, which means our solutions are a -4 and a +5 once we set them equal to 0. Zero product property. Any questions? Way more involved than the other problems that we did. Not necessarily difficult because we've done all the concepts so far, just a little more involved. So the last thing, you need to check for extraneous solutions. So an extraneous solution would be a value that makes the log negative or it makes the log 0. So if you take the number -4 and plug it in for x, I would have the log of -20 and the log of -5. That means x cannot equal -4. That's our extraneous solution. Make sure you cross it off. So you're plugging it in for x and seeing if it makes the log negative. Not all negative x's will make the function negative. It really depends on what quantity you have in the parentheses. So just because this answer is negative doesn't mean that it's extraneous. So make sure you're checking to see, does it make your log negative? If it does, then it's extraneous. If I plug in a 5, 5 minus 1 is 4, 5 times 5 is 25. That one's okay. So x is only equal to 5. Questions? Yeah.
So would the logs individually like determine if they were negative or would the sum determine?
The individual original log. Yes. So you always go back to the original equation with the individual logs. Good question. Because if you plugged it into the sum, it would be positive because they're squaring that number. So if you look at part B has one logarithm. So that means I don't need to condense it. So if there's just one log, you don't need to condense it into a single log because it is a single log. So the only option we have here, Grace, for part B would be, yeah, write it in exponential form. So how would that look, Grace? So 4 to the 5th. That's going to be a pretty big number. Yeah. And when you subtract 624 from that, Grace, what do you get? Yeah. So if I plug the 40 into the original function, the original equation, 10 times 40 is 400. 400 plus 624 is 1024. That remains positive. So when you plug it back into the original function, make sure you're going into that original log form. Does it make this whole quantity 0 or negative? If it does, that's when it's extraneous. If not, then it's your solution as long as you did the algebra correctly. Questions? So there are two more on here with condensing these logs. So anytime you have multiple logs, you've got to condense them into one. They must be condensed in order for us to then change it to exponential form. So we would have the log of 2x times x minus 5 equals 2. So condense first. And then if you want to in the same step, that's fine. Just be careful. My base is 10, so I have 10 squared. And then on the other side, I'm going to multiply so that I'm skipping a step here. So writing it as an exponent because I did condense it. On the other side, I'm just going to distribute to make it 2x squared minus 10x. So I wrote it as an exponent and multiplied in the same step, just to save a little bit of work there. So Faith, what would you take out here to start factoring? Yeah, let's pull out a 2. And then we have -50. So we're looking for two numbers that multiply together to be -50, but add or combine to be -5. You know what they would be, Faith? Yeah, -10 and a +5. So factoring it, there's not a coefficient in front of x squared because we pulled the GCF out. So a -10 and a +5. X is 10 and x is -5. You do not need to show like the step where you separate it and individually set them equal to each other. As long as it's factored and they're both equal to 0, the zero product property enables us to individually solve. So you don't physically need to show you're taking x minus 10 and setting it equal to 0. Zero product property states that. All right, so check to see if they're extraneous. If you plug in that -5, you get a -10 in both cases. So again, you're individually plugging them into the original expression. And if it makes it negative or 0, then it's not a solution. Cross it off. That one's extraneous. So x is equal to 10. We should check the 10 as well, but if I check 10, 2 times 10 is 20, so that's okay. That's not 0 or negative. 10 minus 5 is 5. So again, that one works okay. So going back to the original and just doing a quick check. Questions? So one more equation here. Change the base a little bit. The last two, actually A and C had bases of 10. This has a base of 6, but it doesn't change the method that you're going to use. You still have to condense the logarithms together. But the base is 6 now. So we would have x and then x minus 9. I'm just writing the single x in front of the parentheses. So I know we have to multiply them together because that's how they condense. That's the product property. I'm just pulling the single x term in front of the parentheses. So Julia, how would you write this in exponential form? Yeah, let's just distribute that. So we have x squared minus 9x. Yeah. And if we set it equal to 0, 6 squared, Julia, is 36. So I would have to subtract 36 to the other side. So 6 squared, 36. Set it equal to 0 means we have to take it to the other side. And then we need two numbers that multiply together to be -36. Riley, what do you think? Two numbers that multiply to be -36. Combined to be -9. 2 and 18, 3 goes into 36. 12 or 9. So 3 and 12? Yeah. -12 and a +3. So we have +12 and -3. So again, looking at my X value, if I plug in a -3, I get a -12 there. Cannot take the log of a negative number. So that one would be extraneous, cross it off, circle, box, whatever you prefer to do to the actual answer. 12 works, 12 minus 9 is 3. Questions? So hopefully the homework tonight is still fairly straightforward. We have log equations this time instead of those exponential equations. Just pulling back, it is back in the book, and it's 24 to 38, all of them. I did include the solutions since it is all even and odd. The book only has odd solutions. So the solutions are included, 24 to 38, and then 42. So there's a few problems that you're gonna skip. And then there's number 42 that we will do. Tomorrow we will kind of start reviewing for your test on Thursday. So we will work with some more equations, both log and exponential form. And then we will also start reviewing some of the concepts from the entire chapter, just to start to prepare for that test on Thursday. So we'll kind of do both tomorrow, wrap up the equations, but then also begin solving for Thursday and Friday's test. So remember, Thursday is no calculator. Friday is a calculator test. Questions? And really Friday's portion is like one larger problem and then one smaller. They're 2 word problems really. All right. So if you're at home, have a fantastic day.